the formal general solutions, which we will look at, are not specified in the course. So then I'll also show you a simple way of doing it, which I think is all they're really expecting. So let's start off anyway and have a look at this idea. So if we want to solve sine theta equals something, and they haven't specified, let's go between 0 and 2 pi or something like that, we want to generalise it. Well, first thing we need to know is x positive or is x negative? So if it is positive, we know we could be in the first quadrant. Now if it's the first quadrant, that angle would just be whatever the inverse sine of x is, because if it's a positive number, it's going to give me a positive acute angle as an answer. So I know the acute angle, I can think of that as the inverse sine of x. But if we were solving for every possible solution, there would also be a second quadrant answer. Now that acute angle is still the inverse sine of x, but the answer would be, well, inverse sine of x or pi minus inverse sine of x, whatever that acute angle is. And then of course we could add 2 pi to each of those solutions. Well, that's if x is positive. If x is negative, now if x is negative, then I know I'm in the third quadrant. But the acute angle won't be the inverse sine of x, because x is a negative number. And we said inverse sine of a negative number, we ended up with a negative acute angle. So the actual acute angle will be the inverse sine of negative x. So the acute angle is the inverse sine of negative x. That's in the third quadrant, and of course it could be in the fourth quadrant as well. We end up with pi plus the inverse sine of negative x, or 2 pi minus the inverse sine of negative x. But then we had a rule that we saw yesterday. Inverse sine of negative x is the same as the negative of inverse sine of x, because it was an odd function. So pi plus the inverse sine of negative x is the same as pi minus the inverse sine of x. Well, hang on. That's the same answer we got if x was positive. And the other one, 2 pi plus the inverse sine of x, well, hang on, that's actually the same as inverse sine of x, because we could add 2 pi. So what does that mean? It means it actually doesn't matter whether x is positive or x is negative. We've still got the same solution. So we could generalise it by saying, well, if the sine of theta is x, it'll end up being pi k plus negative 1 to the power of k inverse sine of x. And k is some integer. So that way, if k is an odd number, we know it's minus inverse sine of x. If k is an even number, it'll be plus the inverse sine of x. But that will create every possible solution. All right, let's create the cosine one using the same sort of idea. So if x was positive, first quadrant, well, if x is positive, then inverse cos of x would just give me the acute angle. But it's the fourth quadrant would be the other answer. So my possibility is the inverse cos of x or 2 pi minus inverse cos of x. Now, if x is negative, okay, over there in the second quadrant, but again, inverse cos of negative x is what we're going to need to turn that into a positive number so we get the acute angle. Remember, inverse cos of a negative number would actually give me an obtuse angle. I don't want that. I want the acute angle. So inverse cos of negative x would be the acute angle. And that would be in the second quadrant, because we're saying x is negative. And the third quadrant. Now, in the second quadrant, we'll get pi minus the inverse cos of negative x. The third quadrant, pi plus. Yesterday, we said inverse cos of negative x, that was the one that was an odd function shifted up pi and 2. So we ended up with pi minus the inverse cos of x. Substitute that in. And we end up with, look what happens, the first one becomes the inverse cos of x, same as the other one. The second one becomes 2 pi minus the inverse cos of x, same as the other one. So once again, it does not matter whether x is plus or minus. We can use the same formulas. So, to generalise that one, if cos theta is x, x then I can simply say is 2 pi k plus or minus the inverse cos of x. Because our answers go inverse cos of x, then the next one 2 pi minus, the next one I'd add 2 pi to the first one, so I'd get 2 pi plus, then I'd add 2 pi and get 4 pi minus, but then I'd get 4 pi plus, and so on. So we're always going to get multiples of 2 pi plus or minus whatever the inverse cos of x is. again, k has to be an integer. Right, let's complete the suite. Let's have a look what happens with tan. So if tan is positive, so first quadrant of course, but the other time it's positive is the third quadrant. So we'll have inverse tan of x or pi plus the inverse tan of x. If it's negative, then we have the second quadrant, but again, I want to make that an acute angle, so it'll be the inverse tan of negative x, because x is a negative number. And the fourth quadrant, so we get pi minus the inverse tan of minus x, or 2 pi minus. Inverse tan of negative x, well, inverse tan was an odd function, so inverse tan of negative x is minus the inverse tan of x. We end up with pi plus, same as before, 2 pi plus, well, that's the same as the first one when I've added 2 pi again. So it doesn't matter, sine, cos or tan, doesn't matter, x positive, x negative, we can deal with it exactly the same way. Okay, so tan, but this time it's just going to be multiples of pi plus the inverse tan of x, because our first solution was inverse tan of x, the next one was pi plus the inverse tan of x, the next one will be add 2 pi on, so then I'd have 2 pi plus the inverse tan of x, then I'd have 3 pi plus the inverse tan of x, and so on, and so on, and so on. So I get pi k plus the inverse tan of x, again, k is an integer. So they are the formal general solutions, but as I say, not in the syllabus. So what are they actually expecting from the course now? Let's have a look at some examples. So sine theta equals root 3 on 2, it's one of our exact values, but they haven't specified between 0 and 2 pi. Okay, well, if I was to use the formal definition, I would say, well, it's pi k plus minus 1 to the power of k inverse sine of root 3 on 2. I'd need to specify that k is an integer. And we can work out the inverse sine of root 3 on 2 to make this a bit neater. And I'd say, well, that's as far as I could really go until I start substituting in values for k if I wanted to. But that would create or generate every possible solution for sine theta equals root 3 on 2. That's the formal solution. Okay, if they don't necessarily want us to use that, what are they expecting? Well, in that case, I'd be going, I'll just work out the solution as if it was a right angle triangle, and then we go righto, but I could be in quadrant 1 or quadrant 2, so the same way as you normally would. And I'd go, oh, well, I could get pi on 3 or 2 pi on 3, but of course I can keep going around the circle and add 2 pi to each of those possible answers. That's all they're really expecting. So you solve it as if it is going between 0 and 2 pi, and just simply add 2 pi k to each of those answers where k is an integer. So first one is more a formal, generalised pattern, whereas the second one is simply saying, yeah, I can keep going around the circle. All right, well, let's try this one then. Cos theta is minus 1 on root 2. So let's use the formal one first. So I'd go, well, it's 2 pi k plus or minus the inverse cos of minus 1 on root 2. Now remember, we're playing with the inverse cos function here. Inverse cos of minus 1 on root 2. Well, inverse cos could only give me acute or obtuse angles as an answer. So I can't, for this one, say, oh, well, that'll just be minus pi on, would be minus pi on 4, wouldn't it? It has to be the obtuse angle. So it has to be 3 pi on 4 we use for that. So 2 pi k plus or minus 3 pi on 4, again, where k is an integer. So they'll be using our generalised formula. What are they expecting? They're probably just, again, expecting, oh, well, it'll be in quadrant 2 or quadrant 3. That gives me 2 possibilities, 3 pi on 4 or 5 pi on 4. And again, we could add 2 pi k onto each of those. And let's do a tan one. So 1 on root 3. So plugging it into the formula, we get pi k plus inverse tan of 1 on root 3, which we can work out. That's an exact value. So that would be pi on 6. And there's a formula that would generate every possible solution. What are they expecting? Well, note, for inverse tan, there's actually only one solution I need to do. I don't have to go quadrant 1 and quadrant 3 because the period of tan is pi, not 2 pi. So I don't actually have to go around the complete circle to come up with a possibility. Whereas sine and cosine, the period was 2 pi. So I had to go around the whole circle. So this one here, I really only need the first quadrant. If it was negative, then all I really need would be the second quadrant. So I can go pi on 6 plus pi, go back, and you'll see actually it is the same as the general one in this case. Now what about something like this? Sine of theta is the sine of 5 pi on 7. All right, well, we saw questions sort of like this yesterday, where we said, what was the inverse sine of the sine of 5 pi on 7? We did it like that. So it's the same sort of question. But now they want us to come up with a general solution for this. So I'll plug it into my formula. Pi k plus minus 1k. Now there's that inverse sine of sine. Like I say, our first question is 5 pi on 7. Which quadrant's that in? Right, second quadrant. So I can't just go inverse sine of sine is 5 pi on 7. They don't just cancel each other out, because remember, inverse sine, we can only get acute or negative acute. It's not going to be a negative acute, it's going to be a positive acute, isn't it? Yeah. Cos of 2x is equal to cos pi on 9. All right, so it's a cosine one this time. So I'd go 2 pi k plus or minus inverse cos of cos pi on 9. In this case, pi on 9 is acute, so it's fine. The inverse cos and the cos will cancel, that's fine. But of course that's 2x, so just like any equation, divide both sides by 2, and I'd end up with pi k plus or minus pi on 18, where k is some element of the integers. Cos 4x equals cos x. So 4x is equal to 2 pi k plus or minus the inverse cos of cos x. But hang on, can we just cancel? Oh, someone's saying yes, someone's saying no. Because you don't know. Is x positive or is x negative? So we're going to look at the two cases. If x is positive, then yes, we could just cancel that. Inverse cos of cos would give x. And so the equation becomes 4x equals 2 pi k plus or minus x. Now, moving the x, be real careful here, moving the x to the other side, we change the sign. So it's now 4x minus plus. It probably doesn't really matter, does it? But anyway, but technically, it's minus plus, not plus minus. Giving us 3x is equal to that, and then divide by 3, or 5x would be equal to that. Now, x is now a negative number. So I'm going to get 2 pi k plus or minus pi minus x. You're not going to get x. You get pi minus x. So now, 4x, just because I want to make that x positive, it would be exactly the same as 2 pi k plus or minus. Move it to the other side. So is it the same? Exactly right. So the right-hand side still generates multiples of 2 pi, so there is no need to consider the other cases. So our solution is simply that. 2 pi k on 3 or 2 pi k on 5. Sine 4x equals sine x. 4x equals pi k minus 1 to the k inverse sine of sine x. If it's positive, well then 4x would be pi k plus minus 1 to the k times x. If it's odd, 4x would equal pi k minus x. Right, so there's two things I have to consider here. I've considered it's positive, but now I have to consider whether k is odd or even, because that'll change whether the minus 1 is minus or plus. So it's positive. Now we're considering it's odd. So 4x is pi k minus x, and we go and solve that one. If it's even, I get pi k plus x. That gets me that one. All right, that's if it's positive. If it's negative, well, inverse sine the sine of x, it's still, remember we saw it's still going to be the x. So we're still going to get the same results like we saw when we were proving those general solutions. So actually, we don't need to worry about the positive or negative. What we do have to worry about is the odd or the even. That will make a difference. So no need to check the positive and negatives for the inverse sine there. So there's my final answer. Look, there's a handout there. It's not in the textbook. But there is a handout that the authors of that have put together. So at the end of those sheets, you should find it there.